Um, has anybody got experience with machine learning? Or so, what do you guys do with machine learning?
What we did is we predicted when the speaker will change a topic based on body language and facial expressions.
Yeah. Very interesting.
Yeah.
So I actually worked at a company for 3 years, mostly into predictive analytics.
Mm-hmm.
So I worked on a couple of projects dealing in the healthcare domain and the aviation industry.
Okay.
So like one of them in the healthcare was predicting the revenue leaking out of the healthcare hospitals mostly. So
It's very interesting. Yeah. What did you work on?
It was a project in my undergrad course. It's like we got a video source from CCTV in the shop, and we try to identify the position of the customers in the store.
Mm-hmm. That's very interesting with the, I forgot the name, but Amazon is opening a store. Amazon Go. Everything's called Go nowadays. And yeah, that one is going to be very interesting because it needs to know where the customers are at, like what they're picking from the shelf, and apparently everything's done with computer vision, and I think USC's own Gerard Medioni was working on that, or is working on that very heavily. So he's like definitely one of the major computer vision people in the world, and with Amazon now, like it is doing great research there. And of course, like a loss for USC that he's up there for the moment. I think he's thinking of coming back at some point. Great. So yeah, like lots of different kinds of applications that we can think of with machine learning, and I'd like to start off with like a little bit of motivation of like what is learning, and learning from Merriam-Webster is defined as the activity or process of gaining knowledge or skills by studying, participating, practicing, being taught, or experiencing something. I think this is very, very important, and because we are not programming machine learning algorithms. Well, we're programming them, but then after they're programmed, they learn by themselves. They learn through examples. They learn through iteration and practicing. And the problem is also if a student learns and they get to be asked something completely different, like outside of their domain. So you have a student that learns biology, but then you ask them about quantum physics. They might not be able to like answer the question. And the same thing happens for these machine learning algorithms. They learn about their domain, they learn by examples about their domain, and this is very important because that also gives you an idea of like why the data that you provide to the machine learning algorithm, the examples that it gets to see are so important. So if you focus your the data that the machine learning algorithm sees on one tiny slither of like what the domain data actually could look like, you're missing out on a lot, and the machine learning algorithm might not be able to provide a meaningful response. So data is very, very important, and machine learning algorithms learn through experience and practicing, and through number crunching and like repetition and so on. So how do humans learn? Well, we also learn through repetition. So in elementary school, you had to do all the multiplications and the additions many, many times to understand the concept behind it, to derive rules, to derive an algorithm for that makes sense to you, to understand what's going on. Biology, we have to learn like how molecules or how like evolution works, etc. But also what is happening in the human brain when we learn. Does anybody kind of have an idea, like very high level, nothing like actually what was really going on in the biology. But in a sense, what we're doing, or what's happening in our brain, if we learn new concepts, we learn how to play the piano, we learn, or our brain rewires, and we learn new connections. We learn that some aspects of one part of the brain needs to be connected to another part of the brain. So like new synapses form, synapses get stronger. We connect neurons, and of course this is absolutely false and like not really biologically accurate. But in principle, we learn how to rewire the brain rewires connections, and this is really also what the machine learning algorithms do. So you start off with a randomly initialized neural network, and through examples, through practicing, the neural network will learn what weights are important, what connections, what input data is relevant to my output, to the target that I want to produce. Okay, so it's kind of like a nice analogy, and this is also why they're called neural networks. They learn in a quite similar way that humans do. And how the human brain does it. And so the last item there is like multiplicity of inputs. This is kind of like what we had last semester when we talked about multimodal machine learning. I think, and I have like the class set up in a sense like it, because I think that we learn better if we get like to see the same thing from different aspects as a practical aspect to machine learning. So we have like some assignments, we have a project, there is a verbal aspect to it. Like I would like you guys to be able to talk about it, to be able to form an argument, or to understand what algorithm in what sense is important. I hope I have a couple of examples, so like something visual, something acoustic, that you get from this course as well, to learn different aspects of machine learning. And then obviously, like in the end, there's some aspect of like frontal lecture as well. So this is kind of like the multiplicity of learning that I think is important. And machine learning algorithms similarly sometimes benefit from having multiple sources of information. So if I want to, for example, know the facial expressions of a person, but the person's sitting like this all the time, I'm not able to identify or like know how the mouth looks like, but I might be able to infer if the person's happy or sad by listening to them, okay? Even though I don't see it, but I might hear it. So the multiplicity of inputs can help as well. So machine learning, this is more or less a figure of like how machine learning kind of works, and it has to do with some data sets. So we have here training data, we have test data down here. So in training data is really the data that I have access to while I learn, okay? The test data I do not have access to, and I urge you not to ever use your test data in the training phase, okay? Because this is very, very important that you have a set held out part of your data that can be used for an actual test. Because if you use the same data that you use for training, you've already seen it, you might have overfit, you might have already understood the underlying concept of this data, and are not able to actually extrapolate from the training domain towards the general domain, okay? So test data never used in training. So the training data goes into your machine learning algorithm. That could be anything, right? That could be, for example, we're going to come to that in a little bit. I think for the next lecture, the supervised machine learning part, where one machine learning algorithm could find a threshold. So you have a scale, like you have one-dimensional input, height, right? And you have to define, okay, is this a dachshund based off of the height, or is it, I don't know, like a St. Bernardine, big dog versus small dog, okay? So and you just have the height, and you have a machine learning algorithm that just finds where the threshold is, okay? That could be a machine learning algorithm, simple as that. But it could also be a 20-layered deep neural network that has many, many thousands of parameters. one parameter versus many thousand parameters, okay? So, but this is kind of like what's happening here. So the machine learning algorithm kind of tries to use the data and come up with a hypothesis. While one algorithm comes up with a hypothesis, the threshold for Dachshund versus Saint Bernardine dog is at 2 feet of height, right? That's one hypothesis. But in a deep neural network, for example, the hypothesis is like a huge parameter set. You have all the connections, you have all the weights of your synapses, and so on. And so that's still like the hypothesis of the machine learning algorithm that it comes up with, okay? Does that make sense? And then, once you have defined this hypothesis, you push in with your test data and you want to test your hypothesis, right? So you put in new data points that your hypothesis or your machine learning algorithm has never seen, and then you identify, okay, 90% of the time I'm correct. So my performance metric produces an output. It says 90% of the time I'm correct, or 45% of the time I'm incorrect, or and so on, okay? Or I'm, like, my distance from the target is always in between 0.5 and 0.7. That could be also a performance metric, okay? So depending on your algorithm and your task, you will get different types of performance metrics. And we're going to discuss all of those, or a lot of them, and we'll come up with an idea of like what these mean. But in any case, these performance metrics produce or provide feedback towards your machine learning algorithm, right? And you can use this feedback to either change your algorithm completely, but you can also use it to update your algorithm, okay? And this is kind of like how the process of machine learning in this small domain kind of works. There are a couple of like things that I'm leaving out right now, because obviously if you do this kind of circle multiple times, you're revisiting your test data, you're kind of using your test data in the parameter optimization, so you don't really want to do that. So you would have kind of like two sets, one that you are like validating on continuously, and one data set that you keep out until the very, very, very end, okay? But we're going to come to that. I don't want to make it too complicated right away. All right? So this is kind of like how machine learning sort of works. Are there questions? So the main aspects to this are, like, you have training and test data that you need to have access to. You have your machine learning algorithm that like will try to find a hypothesis. You have to evaluate your hypothesis based off your evaluation, the performance metric that you have. You want to update your machine learning algorithm, and in the end you want to have the best hypothesis that you can come up with, okay? So this is kind of like the idea. In the textbook that we have a nice definition of what machine learning is. It's kind of like machine learning is programming computers to optimize performance criterion using example data or past experience. We need learning in cases where we cannot directly write the computer program to solve a given problem, right? So I don't need machine learning to fetch data from a database. I could use it, but it doesn't really make too much sense, okay? But we need examples or data, or like example data or experience. One case where learning is necessary is when human expertise does not exist, or when humans are unable to explain their expertise. Okay, so when it might be too complicated to put into words, to put into a program what a doctor knows about depression, for example. Like if I ask a doctor, they like, okay, so how do I automatically identify a person with depression? Well, first thing that they're going to tell me is like, use this questionnaire, or like use this interview technique to find out, right? And you have to make an assessment then. Okay, this is too complicated, we don't have access to that. No, they're going to say, okay, they have flat affect. Okay, so flat affect, that means like their facial expressions are mellow, they don't gesture a lot, their like expressivity in the voice is not too like variable, and so on. So there's so many aspects of this that, and I could go on and on, so that it's not really possible to come up with a program to do that, right? But I can interview many people, and I can have a doctor make an assessment and say like, okay, this person's depressed, this one's not, and so on, and then I can use those interviews that I collected for my training data to like learn a machine learning algorithm that then tries to predict if the person is depressed or not. Okay, does that make sense? So most of the time, when we don't have access to defined rules, and but we don't have access to like a strict algorithm or program that goes through, then we want to use machine learning. Okay, so this is kind of like how these machine learning systems will look like for us. Often, and I'm going to refer to this, and I hope, I'm not guaranteeing it, but I hope that the notation will remain the same throughout the lecture. So most of the time, input will be X, and most of the time, outputs will be Y, okay? And most of the time, H will be our hidden variables, like some hyperparameters also. I call them sometimes hyperparameters, sometimes hidden variables. And then theta, these are going to be our model parameters, okay? So what do we do with this? So X is our multimodal or multidimensional, not multimodal in this case, multidimensional input. What could that be? Well, there could be information about the dog's color, the height, the weight, I don't know, the distance between their eyes, and so on. So this could be like these kind of parameters. It could be pixels in a picture, right? Then you have a picture as input. It could be the first pixel, the next pixel, and so on. Okay, these are all inputs that we can have. All right. Does anybody know what the outputs could be? You can have multiple outputs. You can have one output. What could that be?
It could be a classifier, so we can say yes, it's this type of a dog or that type of a dog.
Yeah. So it could be yes or no.
It could be yes or no. That's some sort of decision tree.
Yes, so it could be binary, yes or no. It could be one hot, what people call this now. One hot means that you have. There is, yep. So we have the high-tech class here with actual blackboard. So one hot just means like if we have like multiple outputs here, you code your output as something like this. Okay? So it's just another binary. It's a one hot, like one of these entries is 1 and all the other entries are 0. That would be a one hot vector, so that you can code like 50 classes like that. Okay, you have 50 outputs. And in fact, actually, this is kind of interesting because some of the language models of deep neural networks, they actually do have an output that is as large as the vocabulary. So that could be 100,000 words. So you have 100,000 dimensional outputs. And so you can have that. This happens, and based off of like which one has the highest support, the highest probability, that's the one you're going to choose. Okay, so that's kind of like how these also work. So this can be very large. All right. Another way your output could be coded is just a real value. Okay. So instead of classification, what we're doing here is regression. We try to like predict a number. Okay. It could be between -1 and 1. It could be between 0 and 1. It could be between 0 and 100. That doesn't really matter. Okay. Another way this could look like is you could have an output that looks like this. Jesus. So 0.3, 0.5, 0.2. Okay, and that could be the output of a neural network. So what that would mean is the neural network thinks that this is getting the most support and these are getting less support, but it's not 100% sure. It's like 50% sure it's this one, 30% sure it could be that, 20% could be that one, okay? So you can have these different types of outputs. We're gonna maybe talk about these and called like fuzzy machine learning networks that also get this kind of input. Fuzzy in that context means we as experts, while we feed the data to our system, we ourselves, we don't know if the person has a certain category, like, or is depressed or not. Like the clinician itself is not sure, but they're like, 50% sure, okay? So that's used in those systems where even experts aren't 100% certain. You can also come up with those kind of targets through, for example, crowdsourcing. This is what a lot of people do. Like they show a picture to 20 people and ask, like, is this like a mockingjay or is it a stork or something like that, right? And people just would give their opinions, and you can come up with these fuzzy categories that way as well. Okay. So these are the outputs. Then what are our hidden variables and or hyperparameters? Well, they are hidden from us. So often we don't model them. We just like don't know about them. We can influence them through model selection. We can say, okay, the hyperparameters of or the hidden variables in my problem are like I don't know them. I don't observe them. So even though I want to detect if a person is depressed or not, I don't always have their entire history. So they might have problems at home, or they might just have won something, so they are happier than they're supposed to be. And so these are like the variables that I don't really have control over. Like we don't model those. Yeah, so this is actually kind of, I shouldn't have said that we often also call them hyperparameters, but I should have had another category there. So hidden variables are those that we don't really model, and we don't have access to those. The hyperparameters are parameters of the system. So a neural network has a hyperparameter, for example, the number of layers that it has. Like, is it 1 or 2 or 3? In a support vector machine, we'll get to that. The hyperparameter could be what type of kernel am I using? Am I using a linear kernel or a polynomial kernel or an RBF kernel and so on? So these are kind of like the parameters that we need to optimize for through validation. And then the model parameters are the parameters that we learn in the training, okay? So there are kind of like these two phases to training, to optimization. On the one hand, we optimize model parameters in the training with the training data, but then we can also optimize the hyperparameters with like multiple iterations through our training data. So we select a certain set of hyperparameters and learn them once, then we have optimized it for those hyperparameters, and then we restart completely with a new set of hyperparameters and like optimize for those. And those two systems might have completely different performances. But again, we're going to come to that in more detail later. Okay, so learning in general. So we learn models from data of particular examples. So we choose certain types of like data points that we learn from. We could have pixels, we could have input or like performances or behavior of individuals in a data warehouse, for example. Often like we have loads and loads of data, and but we don't really know what the data actually wants to tell us. So this is kind of like where machine learning comes in, where we have tons and tons of data, but we don't really know what's going on. And actually this is also where this the deep learning comes in, where we have even more amounts of data, but we don't even know what's in the data anymore, and we try to like have the machine learning algorithm identify the representations or the features by themselves, rather than we give the machine learning algorithm information. So an example, in retail, customer transactions to consumer behavior, and we know, for example, people who bought Blink also bought Outliers, which apparently are 2 books on Amazon, and we can come up with these kind of rules by sifting through the data and trying to find, okay, like how many people bought this book Blink and how many bought the book Outliers and so on, okay? So what we want to come up with is a model that is good and useful to approximate this sort of data, all right? So, so what we do is we try to optimize a performance criterion using example data or our past experience. So we had that in the definition. So when we use statistics to create inference from a sample and computer science to come up with efficient algorithms to solve this optimization problem and to represent and evaluate the model for inference. Okay? And I have an example here where basically, for example, in here we want to learn association rules. This is one idea where we can use machine learning. So for example, this is like the simple version of a warehouse analysis or of basket analysis, where so people who typically buy X also buy Y. So if a customer that buys X but not Y, they are a potential customer, so we need to show them advertisement for the item Y, okay? And so what we learn are these conditional probabilities where we want to identify the probability of buying Y given that we have bought X, and we can also provide the machine learning algorithm with some additional information where we would have, for example, D information, which could be demographics. We know if the person is a male or a female customer. We would look at their history. Did they recently buy or look at websites about babies or like cribs or something like that? So maybe they're pregnant, and they might need to. We might need to update the model. Okay, so this is kind of like one example where we would want to find sort of kind of like these rules where we provide the like the Amazon website with information about, okay, so if they bought that, we should show them advertisement for a different product Y. Okay, so this is kind of like one application for machine learning. Another one, more natural one, that is kind of the go-to one for the longest time is kind of like is classification. So we have a certain type of input, and we want to know what the probability is that given an input X, that the target, or like that X is of a certain class Y. So in this example, what we would like to classify is like if an input flower is of one of those 3 classes, and the 3 classes are represented here in red, green, and blue. You have like the sepal length and the sepal width, for example, here. So you can see that if you use this input dimension plus this input dimension, you can pretty much classify easily between the red ones and the green and blue ones, okay? But it doesn't help you identify which of the 2 you are here, right? Because I can't draw a line through here anywhere to separate them clean, okay? Where would I be able to do that? But it's easier in this one here, I think, where we could draw maybe like a line there. We would make some mistakes, but we don't make that many mistakes anymore. We can do a similar thing here. But you see, kind of like the combination of different inputs allows us to separate the classes in different ways, okay? Does that make sense? So what we try to find here is kind of like a separation hyperplane. In this case, because it's 2 dimensions, we kind of try to draw a line. If we had multiple dimensions, 3 dimensions for example, we might find a plane in there that we could separate the classes with. If we are not bound with like linear classifiers, so we don't have to just draw a line, we could maybe draw a curve, right? We could make something else, like we could like learn to separate like this, right? So that would actually be better, right? And would fit better, but what is the difference there? So if I want to not just learn a line, but I learn a curve or like a separation in circles.
Harder to compute.
It's harder, but why is it harder?
The more competition.
So a line is bound by how many variables? 2, right? Then if I wanted to draw any circle, well, it's still kind of 2 variables, right? Like I have a center and I have a radius. But if I want to like have a ellipse or even more complicated ones, I would have to have a center point, a radius in one direction and the other direction, so we can draw an ellipse from that. And so this is kind of like one of the points that we're going to have and next week, where we're going to talk about the power of machine learning algorithms. So you can increase the complexity of your machine learning algorithm, and it will improve on your training data, and it will fit it better. It will learn to separate it more accurately and a lot better, and it might not make any mistakes at all. It might be perfect on your training data, but it doesn't necessarily mean that it's going to be perfect on all the new data that will come in. So if you have a very complex model, it works really well on your training data, but it might not generalize well. It might not generalize to new unseen data because it's so complex and so overfit to your training data that it's not generalizing well. Okay? So just as an example. All right. Moving on. So classification applications or pattern recognition. A lot of people do face recognition, and this is just for completion, so you have like some additional information. We have character recognition, so that would be, for example, handwriting styles, like handwritten digit recognition. People do speech recognition in this area, or medical diagnosis, so symptoms from illnesses, etc. From symptoms to illnesses. And then biometrics also fall into this category, and many more. So this is kind of like a very broad application area for machine learning, so classification or pattern recognition. Okay. So facial expression recognition, just as an example, if you want to do biometrics and you want to re-identify this person here, can you do that in this set of people? Do you find this guy here somewhere?
Yes.
Yeah, so it's this guy, right? And why did you choose this one? It was not the glasses,
Yeah,
like
it's just-
he didn't have the bushy eyebrows and so on. His hair didn't fit here. So you're choosing certain types of features or like patterns in this training set to re-identify the persons. Maybe the nose is like a significant feature for this individual, and but what you also see is we need to learn. We are able to identify this face from this data, even though this picture is not present here, right? So we need to come up with machine learning algorithms that are able to do similar tasks, and these are really hard for machines. Like if you program every single pixel from here into your algorithm, you're not going to re-identify this individual again, because the lighting might have changed, the person might have aged, they might wear like a beard, or they might wear glasses, and so this is kind of like the type of problem that machine learning excels at over other algorithms or other like approaches to this problem. Okay. So this is some type of application that you could do with machine learning. And we humans are really good at this, like recognizing faces, but machines actually start to outperform us in these tasks because like of the amount of data, the complexity of the models, they are becoming a lot better at this than actual humans are.
Would you call the features extracted as inputs or model parameters?
The features that are extracted, I would say they are input, but you're correct, like you could have those as model parameters as well. So the different types of input could be hyperparameters as well. So like for example, do I give the machine learning algorithm access to a certain type of feature or not? So that would be a hyperparameter, so to say. The new approach to this, though, is to just give the image, and the machine learning algorithm will find the features themselves. So at that point, it would not be part of the hyperparameters anymore, or the model parameters. Yeah, but it's a very good question. I think the separation, or like the line, is fuzzy as well. That's a very good point. Yeah. Okay, so this is all classification. What else can we do? We touched upon it briefly. We said like we can do regression. So in regression, what we try to do is kind of like try to predict what's coming next, right? So we have this curve up here. We observe this curve, and there might be some, I don't know, some stock, and we want to know if we should buy or sell, right? So machine learning algorithms actually do this quite a bit right now, and they like do these microtransactions, or like very fast transactions, and sell and buy stock very quickly, and humans do not, like, are not able to keep up with that anymore. And I don't know, I think it was a couple of years ago when I think somebody hacked the Twitter account of like a newspaper, or the I forgot which one it was, and they posted that somebody shot at the White House, and the stock dropped. And so these algorithms read Twitter posts, and they read news articles, and based off of events that are happening right now, they know to sell or buy stock. So this is kind of like what they look at. They look at how the trajectories go, but also how other markets work, how the news, like what's in the news, what's happening right now in the world. So this is kind of like the type of input data that those algorithms get. So this can be very complex. Right, so that's kind of like one idea there. But in general, we want to approximate functions with regression algorithms. Okay, so in this case, the blue line, I hope people see it, is the actual data that we have. Can someone explain the difference between the black and the red line? So which one do you think is closer to the data? The red one, right? So it fits it pretty well. But if you want to do a prediction about the future, would you rather trust the red or the black one? Black one. And can you explain why?
It generalizes better.
It could generalize better.
The outliers.
It doesn't fit to the outliers. And it might be able to more like get at concepts of like what are abstractions of the data rather than like the data itself. So this is very important, okay? And you don't want to have necessarily the best fitting line, but you might want to have a line that learns a good approximation, a good generalization, or a good abstraction of the data. And I have this illustrated a little bit better here as well. So, and this is kind of like the other way around, but you don't want it to be too, not complex enough, right? So in this case, we have these data points, and they follow like this certain pattern, like this parabolic pattern here, where we have a curve happening, but if we try to fit a line into it, we don't really learn the underlying concept of the data. But if we fit the curve into it, we learn the data better, right? And we learn to abstract better. So we really need to find is a good, like a sweet spot between too simple and too complex, okay? That's kind of like where we will navigate around in the future, okay? All right, so in general, also like we're gonna talk about this in more detail later in the class, but supervised learning is one major aspect of machine learning and the types of machine learning that we just had until now. So the data warehouse, the classification, and the regression, these are all supervised tasks, right? So I have the ability to learn my system based off of both input and target output signals, okay? And I know what my model should produce through these target or teacher signals, okay? So the teacher tells my model the performance and how well it does on the current data, okay? So that's important. In unsupervised learning, we would not have access to these kind of teacher signals. They would be gone. So we would have to learn an abstraction just based off of the input data. But here we have both samples X, which are our inputs, plus our target outputs, okay? So, and we want to come as close as possible to those target outputs without overfitting, without underfitting, and so on, with learning a good generalization. So that's kind of like the broad overview. So supervised learning use cases, prediction of future cases, knowledge extraction, we had that with the warehouse, compression, we want to like create more compact representations of the data. We want to identify outliers maybe in fraud or like spam, or hacker attacks versus actual genuine like connection requests on a website and so on, okay? So that's kind of like just as an overview. In unsupervised learning, as a contrast to supervised learning, you don't have access to this teacher signal, you just have access to the data. And what you want to do in this is you want to uncover interesting things, okay, in your data. And so some things in your data could be, for example, clusters of data points. Like these data points are similar amongst each other, so they should be part of one cluster. We had that with the flowers. You had the red ones were very similar towards each other, so maybe they should become one category, even though I don't know that their underlying class is red versus blue versus green, right? But just because of the structure of the data, when you look at it, you could see that there is something common that they have in common, that they're close to each other, versus the other ones were further apart from them, okay? So what you want to do there is you want to uncover structure in your data, and you want to reduce the number of samples to maybe a prototype. So for example, here, this is one of my, like a figure from one of my research papers. We're going to talk about this more, but here we learned the space through like a support vector machine, and what we then did, we wanted to reduce the space into like 5 parameters. Said, okay, here is some space out here, here's something happening, here's something happening, and while red and green are mostly outliers, this one's here very dense, this representation here is very dense as well, and so we use those representations to generate voices, and we're going to come to that later when we talk about unsupervised learning, but this is just an example. We wanted to uncover this kind of like structure within our data. Yeah, so that's kind of like two extremes. Supervised learning, we want to get as close as possible to a target, and unsupervised learning, we want to like uncover structure and information from the data, but without knowing what the class is. And there is something in between, we're going to talk about that as well, which is called semi-supervised learning. That could be used, for example, if there is access to expert knowledge. Like I can ask an expert, like, what is this data point? the expert could tell me exactly what the class is, but that could be very expensive. I don't want to do this on 1 billion data points, I just want to do that on 1,000 data points, okay? So I would get like only 1,000 labels, but all the other data points are not labeled, okay? So that would be one way to use semi-supervised learning, where you don't have all the data points labeled. Okay, and I would like to illustrate why this makes sense in this example. So, what's the question mark? What is that? Is that red or blue? You would guess?
Red if it's based on distance.
Exactly, so I would always kind of like start thinking about stuff based on distance, so let's make it red, right? That looks perfectly fine. So let's ask this question again. What's the label of the question mark? If you see unlabeled data points now, we don't know what these data points are. We only know the labels for 2 red and 1 blue data point. All the other data points we don't know the labels of. But because of the structure, that these 2 points are part of this kind of structure down here, while this point is kind of part of the structure up here, we kind of know, well, there is something going on with this data, and there is a concept that we don't know about yet. And if we only see these data points, we don't know about this concept, right? But if we have all this other data that we don't even have labels about, we can actually infer a different class for the question mark, and we would label it blue, okay? So it's kind of like the motivation why semi-supervised learning makes sense, okay? So in the end, we could label it like that. All right. But there's also other machine learning. We might get to this in the course. Reinforcement learning is another example of machine learning where you actually have an agent and you want this agent to learn a policy for action. If you have, for example, a robot that you have on the table and you don't want the robot to fall off the table, right? So, but you want the robot to explore the entire table. So you would place a robot here and then you would let it like find a way. So first it goes forward, 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 it sees white, 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 white. Now it changes color, what it sees, right? Like, oh, okay. The first time it will try and just fall down, right? Just go further. But then over iterations and iterations, it will learn when it sees something like the color change, that it falls down, that it gets negative reward, it gets punished for what it does. It starts to like change its direction and learn to go left and to go right and so on. So this is kind of like what you try to do with these reinforcement learning algorithms, where you have an agent that explores or that lives in a world that provides it a state, or like it provides it information about what it sees, what's happening in the world, and it provides it rewards. If the robot survives, it gets positive reward over time. If it falls down the table, it gets negative reward, so it knows not to do this the next time. So it tries to learn a sequence of actions that are giving it the most reward. So it's kind of like a soft supervision. It's supervision not based off of like example true false, but it's like, yeah, you're doing 3, you're doing 4, but you're like could be maybe doing 10. But you like unless you explore and you try to find the right actions, you might never experience the highest reward. So the agent has kind of like this intrinsic motivation to identify the actions that maximize the reward. Okay, so that's kind of a brief example of reinforcement learning. Reinforcement learning nowadays has gained a lot of attention, and actually the AlphaGo agent to play Go on a superhuman level actually is based off of deep reinforcement learning. So it learns from examples, it learns from like playing games and games. Alright? So this is another form of machine learning. There are many more, as you can imagine, and we're going to touch on a lot of those. So reinforcement learning, Q learning is down here. We had neural networks. Then there's a subcategory of those are recurrent neural networks. They're kind of similar to hidden Markov models. Expectation maximization can help you identify like a good representation of the data. You like fit, for example, a curve into your data. You have kernel methods, support vector machines, and so on. So there's a lot of different types of algorithms that are available out there. And on Wednesday, I'm going to start talking about examples in my research and other people's work. You can also already kind of look at some of the slides online. I put the slides for this lecture online, but we're at the end for today, and then we're just going to continue on Wednesday. And I'm pretty sure that we're not going to cancel this section. Right? See you Wednesday.